There is an observatory in the highlands of Mexico, about 60 miles southeast of Mexico City, at an altitude of roughly 7,400 feet above sea level. It sits in a valley, surrounded by pine forests and volcanic peaks, and on a clear night, before the city lights grew too close and too bright, the sky above it was extraordinary, not just dark, deeply, profoundly dark, in the way that only high-altitude sites far from city glow can be dark. A sky dense with stars, with the faint smear of the Milky Way arching overhead, with the kind of darkness that makes you feel, instinctively, that the universe is not mostly empty space, but mostly full of something you cannot quite see. Astronomers choose sites like Tonantzintla deliberately. The combination of altitude, dry air, and distance from populated centers produces seeing conditions, a technical term for the quality of the atmosphere through which you are observing, that allow faint objects to be detected that would be invisible from lower, wetter, more light-polluted locations. The ancient light of distant objects, light that has been traveling for millions or billions of years before it arrives at the surface of our planet, can be captured and preserved only under the right conditions. Bad seeing blurs and diffuses that light. Good seeing allows it to be recorded with the precision that makes science possible. In 1942, a Schmidt camera was installed at Tonantzintla. The Schmidt design is not intended for looking closely at individual objects. It is a wide-field instrument designed to photograph large sections of the sky in a single exposure, producing images that cover many square degrees at once. Where a standard telescope might show you a single star in extraordinary detail, a Schmidt camera shows you thousands of stars simultaneously, spread across a wide field, each one faint and small but catalogable. It is the right tool for surveys, for mapping, for the patient, systematic work of going through the sky section by section and recording what is there, knowing that the catalogue you are building will be useful to someone, sometime, for purposes that may not yet be imaginable. The Schmidt camera at Tonantzintla was one of several such instruments operating around the world in the post-war era, a period of remarkable expansion in astronomical observing capability. Photographic technology had improved substantially. Glass plates coated with light-sensitive emulsions could capture images of extraordinary faintness given sufficient exposure time. The technology was not digital. There were no computers to process the images automatically, no algorithms to scan for anomalies, no databases to cross-reference with. There were human eyes, and there were printed plates, and there was the slow, meticulous work of examining them one by one. In 1957, two astronomers at that observatory were doing exactly that kind of work. Their names were Braulio Iriarte and Enrique Chavira. They were photographing blue stars, not for any dramatic reason. Blue stars are hot, and hot stars tend to be interesting in various technical ways that matter to astrophysicists. And so cataloging them was useful science, methodical, patient, the kind of work that fills most of scientific life and receives almost no attention because it is not glamorous and does not make headlines. A catalogue of blue stars seems, in retrospect, like a narrow and specialized thing to produce. But this is the nature of science in practice. The grand discoveries tend not to come from grand expeditions directed toward grand questions. They tend to come from someone carefully doing something specific and unremarkable and noticing in the data something that does not quite fit. The catalogues of the 1950s, produced by patient observers at small observatories around the world, became the raw material for discoveries that would transform astronomy in the decades that followed. Iriarte and Chavira did not know what they were building. They were building something essential. They worked through the catalogue, object after object, most of them exactly what they appeared to be, stars, faint, distant, unremarkable points of light preserved on photographic glass plates. The work had a meditative quality that astronomers of that era sometimes describe with a kind of nostalgia. The long nights at the eyepiece or in the darkroom, the smell of photographic chemicals, the satisfaction of a plate well exposed and cleanly developed, the steady accumulation of data that had not existed before you made it exist. Entry number 618 was a point of light described in their notes as decidedly violet. It was faint. It appeared stellar. It appeared, by every available measure, to be a star. A blue, faint, unremarkable star, photographed in the same way as every other object in the catalogue. No special treatment, no special attention, one of hundreds. There is a concept in the history and philosophy of science sometimes called theoretical blindness, the idea that what you can see is constrained not just by the quality of your instruments, but by the conceptual frameworks you bring to interpreting what your instruments show you. A photographic plate records light. It does not record meaning. The meaning is supplied by the person looking at it, and the meaning they can supply is limited by the vocabulary of concepts available to them. In 1957, the vocabulary did not include quasar. It did not include active galactic nucleus. It did not include supermassive black hole. These were not just terms that had not been coined yet. The underlying concepts, the physical understanding that these terms would eventually name, did not exist. There was no framework in which a faint blue dot on a photographic plate could be recognized as the most luminous object in the observable universe, because the idea that such an object could exist was not part of the scientific landscape. This is not a criticism of Iriarte or Chavira or any of their contemporaries. It is a description of how science works. Science does not progress by scientists failing to see things that are obviously there. It progresses by scientists gradually developing the conceptual and technological tools to recognize phenomena that were previously invisible, not because they were physically hidden, but because there was no framework for understanding them. Ton 618 was invisible in the only way that mattered. It could not be understood. It could be photographed. It could be catalogued. It could be assigned a number. But what it was, what was producing that decidedly violet light, what was sitting at the end of that 10.8 billion light-year journey, could not be known. Not in 1957. Not yet. They wrote it down, filed it away, and forgot about it. What they had photographed was not a star. It was not in our galaxy. It was not anywhere near our galaxy. It was 10.8 billion light-years away, in a direction near the border of the constellations Canes Venatici and Coma Berenices, and it was the most luminous object in the observable universe. At its center was a black hole so massive that our best estimates place its weight at somewhere between 40 and 66 billion times the mass of our Sun. Its event horizon is so large that our entire solar system would fit inside it dozens of times over. The light it was producing at the moment that photographic plate was exposed had been traveling through space since before Earth existed, since before our Sun existed, since before any of the planets in our solar system had formed from the disk of gas and dust surrounding a young star in an unremarkable corner of an unremarkable galaxy. Braulio Iriarte and Enrique Chavira wrote it down and filed it away because they had no way to know what they were looking at. They had the right tools for finding it. They did not yet have the right tools for understanding it. That is a condition we are still in. In 1957, the year that photographic plate was made, Sputnik had not yet launched. The satellite that would begin the space age was still months away from its launch in October of 1957. The idea that human beings might one day stand on the moon was science fiction for most people, and contested science fiction at that. There were physicists and engineers who believed it was possible. There were many more ordinary people who did not. Our understanding of the cosmos in 1957 was extraordinarily limited by current standards, and that limitation was not a failure of intelligence or effort. It was a limitation of tools and time. Astronomy progresses through the instruments it has available, and in 1957, the instruments available were primitive compared to what came later. No space telescopes, no radio telescope arrays of the scale that would be built in the following decades. No computing power sufficient to process large datasets rapidly. No databases in the modern sense. No internet to connect observatories and allow rapid sharing of data. What we knew: galaxies existed. We had understood, since the 1920s, thanks largely to the work of Edwin Hubble, that the fuzzy patches in the sky that had been catalogued as nebulae were not clouds within our own galaxy, but entire separate galaxies, each containing billions of stars, each separated from us by distances so vast that the concept of a mile or a kilometer becomes meaningless. We knew the universe was expanding. We had some rough understanding of its age. Estimates in the 1950s ranged from about 2 billion years to about 10 billion years, closer to the current figure of 13.8 billion than some earlier estimates, but still uncertain. We had some sense of the overall structure, but the deep machinery of the universe, what powered the most extreme objects, what the most extreme objects actually were, was almost entirely unknown. The concept of an active galactic nucleus had not yet been developed. The idea that at the center of many large galaxies there sits a supermassive black hole, and that this black hole, when it is actively feeding on surrounding material, can produce luminosity that outshines the rest of the galaxy by factors of hundreds or thousands, was not in the scientific vocabulary of 1957. The term quasar did not exist. It would be coined in 1964. The term black hole itself did not exist in that form. It would be coined by John Wheeler in 1967. We were doing what all scientists do in all eras. We were cataloging the observable with the tools we had. We were building the databases that later, better-equipped researchers would mine for patterns and anomalies. We were doing the slow, necessary groundwork without which no dramatic discovery is possible. Iriarte and Chavira were laying groundwork. They did not know it. Entry 618 sat in a catalogue for years before anyone asked the right question about it. This is not unusual. It is, in fact, the normal history of astronomy. The most important objects in the universe are often catalogued before they are understood, because the tools for understanding them have not yet been invented. The cosmic microwave background, the afterglow of the Big Bang, was detected accidentally by Arno Penzias and Robert Wilson in 1965, who initially thought the mysterious signal was caused by pigeon droppings on their antenna. Fast radio bursts were detected in archived data years after the original observations, because no one had been looking for them when the data was collected. Gravitational waves were predicted by Einstein in 1916 and not directly detected until 2015. The universe has been throwing things at us for the entire history of astronomy. We have been catching up, slowly, with better and better tools. We were children, staring at the ceiling of a cathedral we did not know was infinite. The space age had not begun. Human beings had never left the surface of the Earth, and the question of whether they ever would was still, in some quarters, contested. We had no satellites. We had no probes. We had not yet visited the moon, had not yet sent anything beyond Earth orbit, had not yet stood anywhere other than the planet we were born on. Our understanding of the universe in 1957 was limited in ways that are difficult to fully appreciate from the vantage point of the present. We knew galaxies existed. We knew the universe was expanding. We had some sense of its age, but the deep structure of how it worked, what powered it, what the most extreme objects in it actually were, was almost entirely unknown. The concept of an active galactic nucleus, the idea that at the center of many galaxies there sits a supermassive black hole that can, when feeding on surrounding gas and dust, produce luminosity that outshines the rest of the galaxy by factors of hundreds or thousands, had not yet been developed. The term quasar did not exist. The term black hole, technically, did not exist either. It would be coined a decade later. We were children, staring at the ceiling of a cathedral we did not know was infinite. This is not a criticism. It is context. The history of astronomy is a history of confronting the unexpected again and again at every scale. Every time we have built a more powerful instrument and turned it toward the sky, we have found things that did not fit our existing understanding, objects that should not exist, processes we had not predicted, scales we had not imagined. The universe has never, at any point in the history of science, turned out to be smaller or simpler than we thought. It has always been larger, always more complex, always stranger. Tonnant-Sinclair entry 618 was waiting for us to develop the tools to understand it. It had been waiting for a very long time. The tools arrived gradually, as they always do. In the 1950s, radio astronomy was still a young field. The idea that astronomical objects could emit radio waves and that radio telescopes could be built to detect them was barely 2 decades old. Carl Jansky had detected radio emission from the Milky Way in 1932. Grote Reber had built the first purpose-built radio telescope in his backyard in Illinois in 1937. The field was developing, but slowly, limited by the technology of the era and by the skepticism of optical astronomers who were not always convinced that radio wavelengths contained scientifically interesting information. The skeptics were wrong. The radio sky turned out to be full of remarkable objects, objects that the optical sky either hid completely or revealed only as faint and ambiguous smudges. Radio galaxies, pulsars, the cosmic microwave background, and quasars. In the 1960s and 1970s, radio astronomy was transforming our understanding of the sky. Radio telescopes were detecting objects that produced enormous amounts of energy at radio wavelengths, objects that appeared stellar in optical photographs, but that could not possibly be stars because their energy output was too extreme and their distances, when measured by the redshift of their light, were too vast. These objects were called quasi-stellar objects. The word was shortened eventually to quasar. The term carries the strangeness of the discovery inside it, even now. Something that looked like a star, but was not a star. Something that produced the light of an entire galaxy from a region smaller than our solar system. In the early 1970s, a radio survey conducted in Bologna, Italy, detected a powerful radio source at the location of the object that Iriarte and Chavira had catalogued 15 years earlier. Something at that position in the sky was transmitting, not faintly, not ambiguously, powerfully, and unmistakably. Ton 618 was a radio-loud quasar. In 1976, an astronomer named Marie-Helene Ulrich pointed a spectrograph at it from the McDonald Observatory in Texas. A spectrograph breaks light apart into its component wavelengths, the same way a prism spreads white light into a rainbow, but with much greater precision and the ability to detect wavelengths far beyond what the human eye can see. By analyzing the pattern of wavelengths in light from a distant object, you can learn an extraordinary amount about what that object is, what it is made of, how it is moving, and how far away it is. What Ulrich saw was a spectrum full of emission lines, bright bands of specific wavelengths produced by particular elements under particular conditions, and those lines were shifted massively toward the red end of the spectrum. The redshift, measured as a value astronomers call Z, was approximately 2.219. This number requires some unpacking because it is easy to say and difficult to feel. A redshift of Z equals 2.219 means that the light we are receiving has been stretched by the expansion of the universe to wavelengths roughly 3 times longer than when it was emitted. It means the light left its source when the universe was about 3 billion years old. The current age of the universe is approximately 13.8 billion years. The light that Ulrich was analyzing in 1976 had been traveling for 10.8 billion years before it entered the spectrograph in Texas. It had left its source before our sun existed, before Earth existed, before any planet in our solar system existed. And the object that produced it was not a star. It was one of the most luminous objects ever detected, a quasar, something feeding, something massive beyond imagination sitting at the center of a galaxy so far away that its distance, expressed in light years, has 10 digits before the decimal point. Entry 618 inches, the Tonnant-Sintler catalogue, a decidedly violet speck on a photographic plate. The brightest object in the observable universe. They wrote it down, filed it away, and forgot about it. It was waiting to be understood. It still is. To understand what Ton 618 is, you first need to understand what it is not. It is not a star. It is not a nebula. It is not a galaxy in any conventional sense, though there is a galaxy at its center, or rather, there is a galaxy wrapped around it, surrounding it, built up over billions of years from the accumulation of matter in a region of space where gravity had a slight advantage. The galaxy is there, we simply cannot see it. It is invisible, not because it does not exist, but because what sits at its center is so luminous that the entire galaxy, with its hundreds of billions of stars, is completely drowned out. The light from those stars is lost, overwhelmed, made invisible by the light coming from a region smaller than our solar system. What sits at the center of Ton 618 is a black hole, but not the kind of black hole that forms when a massive star collapses at the end of its life. Those are stellar mass black holes, ranging from a few times the mass of our sun to perhaps 100 times the mass of our sun. Not the kind you picture when you try to imagine the word. Something small, something dark, something that could be approached without knowing it was there until you were already inside it. The black hole at the center of Ton 618 contains somewhere between 40 and 66 billion solar masses of material compressed into a region defined by its event horizon. It is a different category of object, a different order of existence. And right now, in the period we are seeing it, it is feeding. Here is what happens when a supermassive black hole feeds. The black hole itself produces no light. It produces no radiation detectable from the outside, aside from the theoretical Hawking radiation, which is so faint as to be unmeasurable at these scales. A black hole, in isolation, in the absence of material to consume, is dark, silent, detectable only by its gravitational effects on surrounding matter. But when matter is present, everything changes. Before we get to what happens when matter falls in, it is worth being precise about what a black hole is and is not. because the popular conception of black holes is often misleading in ways that matter for understanding objects like TON 618. A black hole is not a cosmic vacuum cleaner, sucking everything around it inevitably inward. This is a persistent misconception. A black hole exerts gravity exactly like any other massive object. If you replaced our Sun with a black hole of the same mass, our solar system would continue orbiting exactly as it does now. The planets would not spiral inward, the Earth would not be consumed. The gravitational field outside the event horizon of a black hole is identical to the gravitational field of any other object with the same mass. It is only inside the event horizon that the physics becomes extreme. What makes black holes different is not the strength of their gravity at large distances, but the density of their mass. The Sun's gravity is the same whether the Sun's mass is spread across a sphere 870,000 miles in diameter, which it is, or compressed into a sphere about 4 miles in diameter, which it would be as a black hole. But the surface, in the second case, is the event horizon, and below that surface, physics works differently. A black hole also does not emit light. This is important and sometimes confusing because we talk about black holes blazing with energy and producing the most luminous objects in the universe. The black hole itself is dark. The light comes from the material surrounding it, material that has not yet crossed the event horizon, material that is in the process of falling inward and being heated and compressed in that process. The black hole is the engine. The accretion disk is the exhaust. Matter falling toward a black hole does not fall straight in. It has angular momentum, the tendency of moving objects to continue moving in their original direction, which means that instead of plunging directly inward, material settles into a rotating structure around the black hole, a disk, an accretion disk, a flattened, spiraling structure of gas and dust and plasma, slowly working its way inward as friction and magnetic turbulence drain away the angular momentum that would otherwise keep it in orbit. As material in the accretion disk moves inward, it is compressed. Compressed gas heats up. The temperatures in the innermost regions of an active accretion disk reach into the millions of degrees Fahrenheit. At those temperatures, matter does not simply glow, it blazes. It produces radiation across the entire electromagnetic spectrum, from radio waves through visible light, through X-rays, through gamma rays. The energy output is staggering. The efficiency of an accretion disk, the fraction of infalling matter's mass that gets converted to radiation, is approximately 10%. For comparison, nuclear fusion, the process that powers our sun, converts less than 1% of hydrogen's mass to energy. An accretion disk is 10 times more efficient than the process that powers every star in the universe. To feel what this means, consider the following. If you dropped a kilogram of ordinary matter into the accretion disk of a black hole, the energy released would be approximately 9 times 10 to the power of 15 joules. For comparison, the most powerful nuclear weapon ever detonated, the Tsar bomber, released approximately 2 times 10 to the power of 17 joules. The accretion of a kilogram of matter is roughly 1/20th as energetic as the most powerful nuclear weapon in history. If you accreted a ton, the energy release would exceed the Tsar bomber by a factor of 50. Accrete the mass of a small asteroid, say 10 billion kilograms, and the energy released is equivalent to thousands of nuclear weapons detonating simultaneously. TON 618 was accreting at rates equivalent to consuming multiple solar masses of material per year. At that rate, the energy output, 140 trillion times the luminosity of our sun, is almost exactly what the physics predicts. The numbers work. The horror is consistent. And that is before we get to the jets. The jets produced by feeding black holes are among the most powerful phenomena in the observable universe. They are not well understood in the sense that the precise mechanism by which they form and are collimated into tight beams is still an active area of research. The basic picture involves magnetic fields generated by the rotating accretion disk and possibly by the spin of the black hole itself, threading through the infalling plasma and channeling some of it outward rather than inward. The Blanford-Znajek mechanism, proposed in 1977, describes how a spinning black hole can extract energy from its own rotation and channel it into jets. The Blanford-Payne mechanism describes how magnetic fields threading the accretion disk itself can accelerate material outward. Both mechanisms are probably operating in most powerful jets, and the relative contributions of each vary between objects and over time. What is clear is the result. In many active galactic nuclei, magnetic fields, generated by the rotating disk and the spinning black hole itself, channel some of the infalling energy into tight beams of plasma that shoot outward from the poles at velocities approaching the speed of light. These relativistic jets can extend for millions of light years, far beyond the confines of the host galaxy, depositing enormous amounts of energy into the surrounding intergalactic medium, shaping the environment of the galaxy cluster in which they exist. TON 618 is a radio-loud quasar, meaning its jets are producing significant radio emission. The radio signal detected in Bologna in the 1970s was jet emission, energy from a beam of plasma being accelerated to near-light speed by one of the most extreme gravitational environments in the observable universe, crossing 10.8 billion light-years of space and arriving at a radio telescope in northern Italy, faint but detectable. Consider that journey for a moment. The signal began as matter, gas, and plasma falling toward a black hole 40 to 66 billion times the mass of our Sun. The black hole's magnetic field and rotation, through mechanisms still not fully understood, accelerated some of that infalling material into a narrow beam, shooting outward at velocities approaching the speed of light. The beam produced radio waves as the accelerated particles interacted with magnetic fields. Those radio waves spread outward in all directions, including in the direction of what would, billions of years later, become the Earth. As those waves traveled, the universe expanded. The waves themselves were stretched by that expansion. Their original wavelengths, whatever they were when they left the jet, grew longer as space stretched, redshifting them toward longer wavelengths. By the time they arrived at Earth, they had been traveling for 10.8 billion years, and the universe had expanded enough during their journey that the galaxy that produced them was now much farther away than the 10.8 billion light-year distance their light had traveled, carried by the expansion of space to a commoving distance of 18.2 billion light-years. All of that, and the signal was still detectable, faint but real, measurable, real physics, real information, preserved across an incomprehensible journey. This is what radio telescopes do. They catch the ancient, stretched radio echoes of processes that happened billions of years ago and billions of light years away, and they tell us something true about what was there. The luminosity of TON 618 as a quasar is 140 trillion times the luminosity of our Sun. Take a moment with that number. Not just the number itself, but what it means to try to feel a number like that. Human beings are not built to intuitively grasp large numbers. We have a reasonable, intuitive sense of quantities up to perhaps a few hundred. We can picture a room with 200 people in it. We can picture a field with 500 trees. Above a few thousand, our intuitive grasp begins to fail. We can understand large numbers intellectually, we can manipulate them mathematically, but we cannot feel them the way we feel the number 7 or 30 or 250. A million feels approximately as large as a billion in our intuitions, even though a billion is 1,000 times larger. A trillion feels approximately as large as a million, even though it is 1,000,000 times larger. This failure of intuition is relevant here because the numbers describing ton 618 are so far outside the range of human experience that every comparison we make is a kind of translation, an attempt to build a bridge between the measurable and the imaginable. The bridge always falls short. The numbers always exceed the images we use to represent them. With that caveat clearly noted, let us try. Our sun produces enough energy to sustain all life on Earth, to drive weather systems, to power photosynthesis, to warm the surface of a planet, to temperatures compatible with liquid water. It has been doing this for approximately 4.6 billion years, and will continue doing it for approximately another 5 billion years. The Sun is not a particularly luminous star. It sits roughly in the middle of the range of stellar luminosities, but it is the star we know. It is the standard against which we measure things. 140 trillion suns, not 140 trillion stars. 140 trillion suns, each one equivalent to our sun. Each one producing the same energy output that has sustained life on Earth for billions of years. Add those together. Multiply that total energy output by 140 trillion. That is the luminosity of ton 618 as a quasar. The absolute magnitude of ton 618, the measure of its intrinsic brightness on the astronomical magnitude scale, is -30.7. Our sun has an absolute magnitude of +4.8. Every step of 1 unit on the magnitude scale represents a factor of about 2.5 inches brightness. The difference between our sun and TON 618 in terms of intrinsic luminosity is almost incomprehensible. And somewhere inside that blinding flood of energy, there is a galaxy. There are stars. There are probably, given the age and mass of the system, planets. There are clouds of gas and dust that contain the raw materials for chemistry, for biology, for whatever the universe produces when it has time and the right conditions. All of it is there. All of it is invisible, not destroyed, not absent, simply drowned out, overwhelmed by the light from a region that, on the scale of the galaxy, is almost infinitely small. The light from hundreds of billions of stars, lost in the glare of a single feeding black hole. The massive ton 618 is one of the most important and one of the most debated facts about it. Weighing a black hole 10 billion light-years away is not a simple procedure. You cannot put it on a scale. You cannot observe it directly. You can only measure its gravitational effects on the matter surrounding it, and from those measurements, infer the mass that must be present to produce those effects. The primary method used for ton 618 is called the virial mass method. It works like this. Gas orbiting near the black hole moves at a speed determined by the gravitational pull of the black hole. Faster orbital speeds mean stronger gravity. Stronger gravity means more mass. You can measure the orbital speeds of this gas by looking at the width of the emission lines in its spectrum. Gas moving toward you shifts the wavelengths of its emitted light toward shorter, bluer wavelengths. Gas moving away from you shifts them toward longer, redder wavelengths. Gas orbiting a massive object is doing both simultaneously on opposite sides of the orbit, and the result is that emission lines appear broadened spread out across a range of wavelengths rather than appearing as a sharp, thin spike. The broader the line, the faster the gas is moving. The faster the gas is moving, the more massive the black hole it orbits. In 2004, astronomer Ohad Shema and colleagues used the H-beta emission line to estimate the mass of TON 618's central black hole. The H-beta line was broad, very broad. The gas producing it was moving at approximately 6,500 miles per second. From this, they estimated the mass at approximately 66 billion solar masses. In 2019, a separate group, led by Gay and colleagues, used a different emission line, the carbon IV line, to make their own estimate. The C4 line is produced by different gas, in a different region around the black hole, and it yielded different gas velocities, approximately 1,715 miles per second. Their estimate: approximately 40.7 billion solar masses. Same object. Different measurements, different methodologies. Results that differ by a factor of more than 1.5. Both measurements have uncertainties. The virial mass method makes assumptions about the geometry of the gas distribution, the relationship between the broadline region and the actual gravitational sphere of influence, and the calibration of the mass-velocity relationship. These assumptions introduce systematic uncertainties that are difficult to fully quantify. The true mass of TON 618 is somewhere within the range, defined by these two measurements, and possibly outside it. The current scientific consensus uses a range of 40 to 66 billion solar masses, acknowledging honestly that we do not know the precise value. The margin of error in our mass estimate for TON 618 is larger than the total mass of many galaxy clusters. We are uncertain by tens of billions of solar masses about how massive this object is. And even at the low end of that range, it is the most massive confirmed black hole in the observable universe. Imagine trying to weigh something you cannot see from 10 billion light-years away using only the color of light. That is essentially what we are doing. The fact that we can do it at all with any precision is a triumph of human ingenuity. The fact that our two best attempts differ by 25 billion solar masses is a reminder that the universe does not make precision easy. Numbers at the scale of TON 618 stop working the way numbers are supposed to work. This is not a failure of mathematics. It is a failure of human intuition, which was built for a world of rocks and rivers and distances that can be walked. When we try to extend that intuition to objects 40 billion times the mass of our Sun, or to distances measured in billions of light-years, the cognitive machinery simply does not produce the right outputs. The numbers are technically correct. They do not feel like anything. So, let us build this up slowly. Let us start where our intuition works and move outward, one step at a time, until we arrive somewhere that the machinery breaks down entirely. That breakdown is informative. It tells you something true about the universe. Start with Earth, a sphere approximately 7,900 miles in diameter. The distance across it from one side to the other is something we can travel. Airplanes cover it in roughly a day. It is large. On a human scale, it is enormous, an entire planet. Billions of tons of rock and metal and water and life. The Sun is larger. The Sun is approximately 870,000 miles in diameter. That is about 109 Earths placed side by side. If you replaced our Sun with a hollow sphere, you could fit approximately 1.3 million Earths inside it. The Sun is massive. It contains 99.86% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, every speck of dust, all of it combined, accounts for only 0.14% of the solar system's total mass. Now move to the scale of the solar system. The distance from Earth to the Sun is defined as 1 astronomical unit. The distance from the Sun to the outermost planet, Neptune, is approximately 30 astronomical units. The distance from the Sun to Pluto, which we now classify as a dwarf planet, but which still defines, in our imaginations, the outer edge of the familiar solar system, is approximately 40 astronomical units. Beyond Pluto, at distances ranging from perhaps 2,000 to 100,000 astronomical units, lies the Oort cloud, a theoretical shell of icy bodies that are the source of long-period comets. We have never directly observed the Oort cloud. We infer its existence from the orbits of comets that occasionally drop inward toward the Sun. The outer edge of the Oort cloud represents, in some meaningful sense, the outer boundary of the Sun's gravitational dominance. The distance at which things can still be said to orbit our Sun, rather than the galaxy, that is the solar system. Earth to the Sun, 1 astronomical unit. Sun to Pluto, 40 astronomical units. Sun to the outer Oort cloud, perhaps 100,000 astronomical units. Now, let us talk about TON 618's event horizon. But first, let us talk about what an event horizon is. Because the word horizon is used in astronomy in several different ways, and in the case of black holes, it refers to something specific and strange enough that it deserves careful description before we attach numbers to it. In ordinary experience, a horizon is the line where the sky meets the ground. The furthest distance you can see before the curvature of the Earth hides what lies beyond. It is a perceptual limit, dependent on your height and the curvature of the surface you stand on. If you climb higher, the horizon retreats. If you descend, it approaches. The horizon is not a feature of the landscape, it is a feature of your position in it. The event horizon of a black hole is different. It is not a perceptual limit, it is a physical one. It is the boundary within which the escape velocity from the gravitational field exceeds the speed of light. Escape velocity is the speed at which an object must be moving outward to escape the gravitational pull of a massive body. For Earth, the escape velocity from the surface is approximately 7 miles per second. For our Sun, it is approximately 383 miles per second. For a black hole, there is a distance, the event horizon, at which the escape velocity reaches 186,000 miles per second, the speed of light. Inside this distance, even light, moving at the maximum speed the universe permits, cannot escape. Nothing can. There is no speed above the speed of light. There is no faster escape route. Once inside the event horizon, nothing returns. The event horizon is not a material boundary. You would not feel it if you crossed it. It is not like a wall or a surface. It is a region of space-time, defined by geometry and gravity, with no physical substance. The space inside the event horizon is, locally, just space. It does not look different. It does not feel different at the moment of crossing. It is simply the point of no return. For most black holes we can imagine encountering, the event horizon is extraordinarily compact. The event horizon of a black hole with the mass of our Sun would have a radius of approximately 2 miles. The event horizon of Sagittarius A star, with its 4.3 million solar masses, has a radius of approximately 7.5 million miles, about 1/10 of the Earth-Sun distance. Large by human standards, invisible on the scale of the solar system. TON 618 is different. The event horizon of a black hole is defined by the Schwarzschild radius, the distance from the center at which the escape velocity equals the speed of light. Inside this radius, nothing, not matter, not light, not any signal of any kind, can escape the gravitational pull and reach the outside universe. The event horizon is not a physical surface. It is not a wall. There is no material boundary there, nothing you would collide with if you crossed it. It is a mathematical surface, a threshold in space-time, beyond which the physics of inside and outside become irreconcilably different. For a black hole of 66 billion solar masses, the Schwarzschild radius is approximately 1,300 astronomical units. For the lower mass estimate of 40.7 billion solar masses, the radius is approximately 800 astronomical units. Let those numbers connect to the ones we just established. The distance from our Sun to Pluto is 40 astronomical units. The event horizon of TON 618 on the higher mass estimate extends to 1,300 astronomical units. That is more than 32 times the distance from the Sun to Pluto. Our entire solar system, Mercury to Pluto, fits inside the event horizon of TON 618 with room to spare. If you need a moment with that, take it. It does not get less strange the second time. Our entire solar system, including Pluto, including the scattered disk, including much of the inner Oort cloud, fits inside the event horizon of TON 618, not once, but more than 30 times over. If you replaced our Sun with TON 618, the event horizon would engulf Mercury in the first second of expansion, Venus shortly after, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, the Kuiper belt, the inner Oort cloud. The event horizon would extend far beyond anything we have ever visited, beyond anything we have ever sent a probe to, beyond the outermost boundaries of the solar system we inhabit. Light crossing from one edge of this event horizon to the other, traveling at the speed of light, would take weeks. Let that sink in for a moment. Not seconds, weeks. Light, the fastest thing in the universe, traveling for weeks to cross the diameter of a boundary within a single black hole. Think about what light can do in a week. In 1 second, light travels approximately 186,000 miles, which is about 23 times the circumference of Earth. In 1 minute, light covers 11 million miles, roughly the distance from Earth to Venus at its closest approach. In 1 hour, light covers just over 620 million miles, enough to reach beyond Jupiter. In 1 day, light travels approximately 16 billion miles, roughly 173 astronomical units, more than 4 times the distance from the Sun to Pluto. In 1 week, light travels approximately 112 billion miles, roughly 1,200 astronomical units. The distance from the center of TON 618's event horizon to its edge, that is the radius. The diameter is twice that. Light takes approximately 2 weeks to cross the full diameter of the event horizon of TON 618. 2 weeks of traveling at the speed of light to cross what is, by the standard of the observable universe, a tiny, localized object at the center of a single galaxy. And here is the thing about that event horizon. You could be inside it and not know. The boundary is invisible. There is no marker, no sign, no physical feature that distinguishes the inside from the outside at the scale of the crossing. The space inside is, locally, just space. The curvature is gentle at the scale of a human body. The tidal forces are negligible. You could cross the event horizon of Ton 618, the boundary beyond which nothing returns, and your immediate experience would be indistinguishable from floating in empty space. The universe would look the same. Stars in every direction. The distant glow of the host galaxy perhaps visible. Nothing to suggest you had just made the most consequential transition possible in physics. From a future with options to a future with only one destination. The quiet horror of Ton 618 is not in its size, though the size is horrifying. It is in this detail. The most dangerous place in the observable universe is a place you could enter without knowing. It looks like nothing. It feels like nothing at the moment of crossing. And it is inescapable. And Ton 618 is not the only black hole. It is not the only supermassive black hole in the universe. It is not even the only supermassive black hole in our cosmic neighborhood, in the sense that astronomers use that term for regions measured in millions of light years. Let us put it in context. At the center of our own galaxy, the Milky Way, there sits a supermassive black hole called Sagittarius A star. We have been able to study it in extraordinary detail over the past few decades, tracking the orbits of stars very close to the galactic center, watching them move in tight ellipses around an invisible point. From those orbits, we have determined that Sagittarius A star has a mass of approximately 4.3 million solar masses. It was directly imaged for the first time in 2022, revealing the shadow of its event horizon against the glowing gas that surrounds it. 4.3 million solar masses. That is a large number, a remarkable object, an entire mass equivalent to 4 million of our suns, compressed into a region so small that it has an event horizon with a radius of approximately 7.5 million miles, roughly 1/10 the distance from the Earth to our Sun. Ton 618 is more than 15,000 times more massive than Sagittarius A star. In 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, that of the supermassive black hole at the center of the galaxy M87, approximately 53 million light-years away. That image, a bright ring of orange-gold light surrounding a dark central region, became one of the most widely reproduced scientific images in recent history. The black hole at the center of M87 has a mass of approximately 6.5 billion solar masses. Its event horizon is large enough to contain our solar system. When that image was released, commentators described it as the most extreme object ever directly observed. Ton 618 is 10 times more massive than the black hole at the center of M87. The Milky Way, our entire galaxy, with its 200 to 400 billion stars, with its dark matter halo, with its gas and dust and stellar remnants, has a total mass of approximately 1 to 2 trillion solar masses. But most of that mass is dark matter, which we cannot see and about which we know very little. The mass in ordinary matter, in stars and gas and dust, is estimated at approximately 64 billion solar masses. Ton 618, at the high end of its mass range, has a mass comparable to all the ordinary matter in the Milky Way concentrated into a single object. Let us add one more comparison, one that captures something important about the relationship between Ton 618 and the structures it exists within. The observable universe contains an estimated 2 trillion galaxies. Each of those galaxies contains, on average, somewhere between 1 billion and 1 trillion stars. The total number of stars in the observable universe is estimated at around 1 septillion, which is a 1 followed by 24 zeros. The combined mass of all those stars, all those suns, all those points of light that constitute the visible structure of the cosmos is roughly 2 × 10 to the power of 23 solar masses. Ton 618 is one black hole, one object, with a mass of up to 66 billion solar masses. It is a small fraction of the total mass of the universe. It is not a large fraction. The universe is incomprehensibly more massive than any single object within it. But the point is not the fraction. The point is the density. The point is that all of that mass, 40 to 66 billion solar masses, exists in a region defined by an event horizon. An event horizon that you could cross without feeling it. An event horizon that contains our entire solar system inside it dozens of times over. The mass is not impressive because it is a large fraction of the universe. It is impressive because of the density of the accumulation. The fact that the universe, in one location, concentrated this much mass into a single object in the first 3 billion years of its existence, in ways that our current physics cannot fully explain. The comparison cascade does not end there. In 2019, the Event Horizon Telescope produced an image that was broadcast around the world, a blurry orange ring of light surrounding a dark central region. The black hole it showed, M87 star, is approximately 53 million light-years away in the galaxy Messier 87, a giant elliptical galaxy that is one of the most massive galaxies in the nearby universe. M87 star has a mass of approximately 6.5 billion solar masses. When that image was released, it was described in headlines as showing the largest black hole ever imaged, the most extreme object ever directly observed. Ton 618 is 10 times more massive than M87's star. There is one other object worth mentioning, a black hole called Phoenix A at the center of the galaxy cluster Abell 2029. Some estimates have placed its mass as high as 100 billion solar masses, which would make it significantly more massive than Ton 618. But those estimates are highly uncertain, disputed in the literature, and may reflect systematic errors in the measurement methodology. Phoenix A is a mystery. It may be larger than Ton 618. It may not be. The data is not conclusive. The universe, as always, reserves the right to surprise us. Ton 618, by the current scientific consensus, is the most extreme confirmed case of a category that did not have a name until relatively recently. Astronomers have begun using the term ultramassive black holes to refer to objects above roughly 10 to 40 billion solar masses, a category distinct from supermassive black holes, not just in degree, but in the questions they pose about how the universe works. Ton 618 sits at the top of that category. Fewer than a dozen confirmed ultramassive black holes are known. Ton 618 is the most extreme of them. But here is the detail that changes everything about how we interpret everything we have just described. We are not seeing TON 618 as it is. We are seeing it as it was. The light we observe, the radio waves, the visible photons, the X-rays that have been analyzed by astronomers over the past 50 years, that light left Ton 618 approximately 10.8 billion years ago. It has been traveling through space since before our solar system formed, since before our sun ignited, since before the Earth condensed from a cloud of gas and dust around a young star in an unremarkable region of an unremarkable galaxy. Every image, every spectrum, every measurement, every number we have discussed, all of it is archaeology, not astronomy. We are studying the fossil light of an object as it was in the distant past, and inferring from that fossil what the object might be now. The word now is worth examining when we talk about objects at cosmological distances. It is one of those words that seems simple until you push on it and then reveals itself to be deeply strange. In ordinary life, now means something clear and immediate, this moment, the shared instant. When you have a conversation with someone in the same room, you are both experiencing now simultaneously, or close enough to simultaneously, that the difference is physically negligible. When you look at something, you are seeing it as it is. The speed of light is so much faster than anything in ordinary human experience that the delay between an event and your perception of it is invisible. But the universe is not a room. The universe is not even a planet or a solar system or a galaxy. The universe is a structure 93 billion light-years across in the observable part alone, and light, for all its speed, takes time to cross that structure. And while light is crossing it, the universe continues to evolve. Events happen. Things change. The image of a distant object that finally arrives at your telescope is not an image of that object as it is. It is an image of that object as it was, at the moment the light left it, which may have been long before your telescope existed, long before the mountain it sits on was formed, long before the solar system that contains your planet was born from a collapsing cloud of gas. This is not a metaphysical point. It is a physical one, with practical consequences for how we understand the universe and everything we observe in it. This moment, the present, the shared instant we all inhabit together. When you look at the person across from you, you are seeing them as they are now, or close enough that the difference, the fraction of a microsecond it takes light to cross the room, is irrelevant. When you look at the sun, you are seeing it as it was approximately 8 minutes ago. The light takes that long to travel from the surface of the sun to your eyes. If the sun were to suddenly stop shining, you would not know for 8 minutes. When you look at the nearest star beyond our sun, Proxima Centauri, you see it as it was approximately 4.2 years ago. It is possible, in principle, that Proxima Centauri has undergone some dramatic change in the past 4 years, and we would not yet know. When you look at the Andromeda Galaxy, you see it as it was approximately 2.5 million years ago. Modern humans, Homo sapiens as a species, did not yet exist when that light left Andromeda. When you look at TON 618, you see it as it was 10.8 billion years ago, when the universe was approximately 3 billion years old, roughly 20% of its current age. The universe was different then. Not just quantitatively different, not just younger or smaller, but qualitatively different in ways that are difficult to fully convey. Galaxies were younger. They had not yet used up their supplies of cold gas, the fuel for star formation. The rate of star formation across the cosmos was perhaps 10 to 30 times higher than it is today, meaning that new stars were being born at a rate that would seem extraordinary by current standards. Many of these young stars were massive and hot, pouring ultraviolet radiation into their host galaxies and into the intergalactic medium, contributing to a process called reionization that transformed the neutral hydrogen, filling the early universe into the ionized plasma that fills the vast spaces between galaxies today. The intergalactic medium itself was different, denser, more turbulent, crossed by streams and filaments of gas flowing along the scaffolding of the cosmic web, the vast network of dark matter filaments that had grown from tiny density fluctuations in the first seconds after the Big Bang. Galaxies were forming at the intersections of these filaments, accreting gas from their surroundings, building up their stellar populations, developing the central black holes that would eventually become the quasars we observe. Mergers between galaxies were more frequent. The universe was smaller in the sense that galaxies were, on average, closer together, because space had not yet expanded to its current extent. The rate of close encounters and collisions between galaxies was higher than it is today, and those collisions drove gas inward toward galactic centers, fueling the black holes that sat there. It was a violent, energetic, productive universe. Not in the human sense of those words, but in the cosmological sense. Matter was actively organizing itself into the structures we see today. The cosmic web was being drawn, thread by thread, out of the initial near uniformity of the early universe. Galaxies were being built. Stars were burning through their fuel at prodigious rates. And in some galactic centers, black holes were consuming gas at rates that would produce the blazing quasars we see when we look back at that era. The intergalactic medium was denser, more turbulent, filled with streams of gas flowing between forming structures along the scaffolding of the cosmic web. It was an early, energetic, chaotic universe. And in that early universe, Ton 618 was blazing. Quasars are not permanent features of the universe. They are phases. A quasar shines when its central black hole is actively feeding, when there is a supply of gas falling inward, producing the accretion disk and the jets and the blinding luminosity, when the gas supply is exhausted, or when the feeding rate drops below a certain threshold, the quasar dims and eventually goes dark. The galaxy that hosts it becomes an ordinary galaxy, perhaps a little more massive than average, perhaps with an unusually large central bulge of stars, but otherwise unremarkable. The black hole at its center persists. It does not go anywhere. It does not evaporate on any relevant timescale. It simply sits there, no longer feeding, no longer producing the extreme luminosity that made it visible across the observable universe. Quasars were far more common in the early universe than they are today. The epoch between about 2 and 3 billion years after the Big Bang, the period we are observing when we look at Ton 618, was the peak of quasar activity across the cosmos. Galaxies were full of cold gas. Black holes were growing rapidly. The interactions between forming galaxies were frequent, and these interactions drove gas inward toward galactic centers, fueling the black holes that sat there. The universe was, in a very real sense, louder then, brighter, more violent. The number of active quasars per unit volume of the cosmos was perhaps 1,000 times higher than it is today. Since that peak, quasar activity has declined steadily. Galaxies have used up their cold gas reserves. Interactions between galaxies have become less frequent as the universe has expanded. The era of the great quasars is largely over. The universe is quieter now, though not silent. There are still active galactic nuclei, still quasars, still black holes feeding at the centers of some galaxies. But the density of them has declined dramatically from the cosmic noon of quasar activity that coincides with our observation of Ton 618. This is the context in which Ton 618 blazed. It was not an anomaly in a quiet universe. It was an extreme example of a common phenomenon in a violent, energetic, actively forming universe. The most extreme example we know of, but surrounded in that epoch by others of its kind, each one a black hole consuming its galaxy's gas supply and pouring that energy out as radiation across all wavelengths. That era is over. The evidence for it is preserved in the light that is still arriving from that period, the fossil light of a universe we will never be able to revisit, that we can only observe across the distance of billions of years. Ton 618's quasar phase has almost certainly ended. The object we observe, that blazing point of light 140 trillion times the luminosity of our Sun, represents a moment 10.8 billion years in the past. In the universe as it exists today, TON 618 is almost certainly quiet. The accretion disk has drained, the jets have switched off, the host galaxy, now visible to itself, without the blinding glare of the active nucleus, has gone through billions of years of evolution, consumed its gas, formed generations of stars, grown old. The black hole is still there. It will always be there, for any practical definition of always. Nothing that happens in the universe on timescales we can meaningfully contemplate will affect a black hole of this mass. It simply sits at the center of what was once a blazing quasar and is now a quiet, massive galaxy, waiting, dark, patient, indifferent to time in the way that only the most extreme objects in the universe can be. We will not live to receive the light that would tell us what TON 618 looks like today. The light that left TON 618 at this moment, if there is any light to speak of, will not reach Earth for approximately 10.8 billion years. The Sun will have exhausted its nuclear fuel long before then. The Earth will no longer exist in any recognizable form. Whatever inherits the solar system, if anything does, will receive that light. The most massive confirmed example of the most extreme type of the most extreme class of object in the known universe. And yet, it is not just an object to be catalogued and measured and placed in a hierarchy. It is a puzzle. It is a contradiction. It is something that challenges the models we use to understand the universe. Something that, in its very existence, tells us that our physics is incomplete. We will come to that. We are seeing a ghost, a fossil, a record of something that happened in the deep past, preserved in photons that have been traveling through the expanding universe for longer than the Earth has existed. There is a further complication, one that reveals something profound about the nature of the universe we inhabit. The observable universe has a boundary, not a wall, not an edge, a horizon defined by the speed of light and the age of the universe. We can only see objects whose light has had enough time to reach us since the universe began. Anything beyond that horizon, and there is certainly something beyond it, is invisible to us. Not because it does not exist, because its light has not yet arrived. The observable universe extends to a radius of approximately 46 billion light-years in every direction. That number seems strange, given that the universe is only 13.8 billion years old. Should not the edge of the observable universe be 13.8 billion light-years away? The distance light could have traveled in that time? The answer is no, because the universe has been expanding while that light was traveling. Space itself has stretched, carrying distant objects further from us than the distance their light has traveled. The universe is larger than the distance light has covered in its lifetime, because the metric of space itself has expanded. TON 618 sits at a co-moving distance of approximately 18.2 billion light-years. It is deep in the observable universe, near its outer limits, not at the edge, but well past the halfway point in terms of the most distant objects we can observe. The universe is still expanding. Every object in it, on large enough scales, is moving away from every other object. TON 618 is moving away from us, not through space in the ordinary sense, but with the expansion of space itself. The rate of that recession, at TON 618's distance, is significant. The light we will receive from it in the future will be redshifted to even longer wavelengths, arriving from an ever more distant past. There is a concept in cosmology called the cosmic event horizon, distinct from a black hole's event horizon. It is the boundary beyond which objects are receding from us faster than the speed of light due to the expansion of space, such that no light they emit will ever reach us. Some objects we can currently observe will eventually cross this boundary and become permanently invisible to us, not because they have been destroyed, but because the expansion of space will carry them beyond our ability to see them. We are gradually, cosmically, being isolated. The observable universe is not growing, it is shrinking. Objects are leaving it, one by one, as the expansion of space accelerates. We are on an island of light. Beyond it, events are happening that we will never witness. Objects exist that we will never detect. The universe is not hiding from us. It is simply indifferent to our ability to look. Here is the central mystery of TON 618. The thing that makes it not just an extreme object, but a genuinely troubling one for our understanding of how the universe works. It should not be this massive. Not yet. Not at the time we are observing it. This is a strong statement, and it is worth being precise about what it means. It does not mean that TON 618 is impossible in some absolute sense. It clearly exists. We have measured it. We have its spectrum, its luminosity, its redshift. It is real. What the statement means is that our current models of how black holes grow cannot produce an object this massive in the available time, starting from any seed we know how to make. That is a different kind of problem. Not impossibility, inexplicability. And inexplicability in science is always interesting. To understand why, you need to understand something about how black holes grow. A black hole grows by consuming matter. Matter falls in, the mass of the black hole increases, the event horizon expands outward. Simple enough in principle. But there is a fundamental physical limit on how fast this process can proceed, a limit set not by the strength of gravity, but by the behavior of radiation. When matter falls into a black hole, it does not fall silently. The accretion disk it forms is blazingly hot, and hot things radiate. That radiation pushes outward, away from the black hole. If the accretion rate is high enough, the outward radiation pressure equals the inward gravitational pull. At this point, called the Eddington limit, any additional infalling matter is blown away by the radiation before it can reach the event horizon. The accretion process becomes self-regulating. Feed too fast, and the radiation from your own meal blows away the rest of your food. The Eddington limit sets a maximum rate at which a black hole can grow through accretion. For a black hole of a given mass, there is a specific maximum luminosity, and therefore a specific maximum accretion rate that can be sustained indefinitely. If you start with a seed black hole, perhaps a few hundred solar masses left over from the collapse of a massive early star, and allow it to accrete at exactly the Eddington rate, starting from the Big Bang and continuing without interruption, how massive can it grow by the time the universe is 3 billion years old? The age of the universe, when we observe TON 618, the answer, working through the exponential growth equations, is a few billion solar masses, perhaps 10 billion, with generous assumptions, not 40 to 66 billion. To grow to TON 618's observed mass in the available time, starting from any seed black hole that our models can produce, requires either periods of super-Eddington accretion, meaning feeding rates higher than the theoretical maximum, or a starting mass far larger than any ordinary stellar collapse can produce, or both. There is also a second constraint that makes this even more pointed. In 2015, the physicist Andrew King calculated a theoretical upper limit on the mass that a black hole can reach through accretion alone. For a non-spinning black hole, that limit is approximately 50 billion solar masses. The argument is subtle but rests on the fact that at very high masses, the radiation produced by accretion is so extreme that it disrupts the supply of infalling gas before it can reach the event horizon, effectively halting growth. Ton 618, at the high end of its mass estimate of 66 billion solar masses, may exceed this theoretical limit. It may be more massive than a black hole has any right to be. So how did it get here? The honest answer is that we do not fully know. Several mechanisms have been proposed, and each of them has problems. The first proposal is super-Eddington accretion. Perhaps the Eddington limit is not as hard a ceiling as the simple theory suggests. In the chaotic environment of the early universe, where gas was abundant, dense, and turbulent, black holes may have been able to feed at rates significantly above the theoretical maximum, at least for limited periods. Simulations of early universe black hole growth have shown that brief episodes of hyper-Eddington accretion are possible under the right conditions. If Ton 618's ancestors experienced multiple such episodes, the cumulative growth could, in principle, produce the observed mass. The problem is that sustaining the necessary accretion rates for long enough across billions of years remains extremely difficult to reproduce in models. The second proposal involves what cosmologists call direct collapse black holes. In the ordinary course of stellar evolution, stars form when gas clouds collapse, heat up, ignite nuclear fusion, and eventually die as compact remnants. The most massive stars end as black holes of perhaps a few tens of solar masses. These stellar remnant black holes then need to grow through accretion, which takes time and faces the Eddington limit. But in the very early universe, under special conditions that are thought to have existed in some regions, this sequence of events may have been bypassed. If a gas cloud was massive enough, and if conditions were such that it could not fragment into stars and instead collapsed directly, the result might have been a black hole of 100,000 to 1 million solar masses formed almost instantaneously. A direct collapse black hole. With 1 million solar mass seed instead of 100 solar mass seed, growing to 40 or 66 billion solar masses in 3 billion years, becomes much more plausible, though still challenging. The problem with direct collapse is that the conditions required for it to happen seem quite specific and may have been rare. Whether enough direct collapse events occurred to produce the observed population of ultramassive early black holes is an open question. The third proposal involves mergers. In the dense environment of the early universe, where galaxies were forming and interacting and colliding, black holes at galactic centers would have participated in those mergers. When two galaxies merge, their central black holes eventually sink together through dynamical friction and merge as well. A rapid sequence of major mergers could in principle boost a black hole's mass dramatically in a relatively short time. The problem is that the merger process is limited by the timescale on which black holes sink to the center of the merged galaxy, which is not instantaneous and may not be fast enough to explain the most extreme early objects. The fourth, and most exotic, proposal involves primordial black holes. In the first second after the Big Bang, density fluctuations in the universe may have been large enough in some regions to directly collapse into black holes without the intermediary of stars or gas clouds. These primordial black holes could have formed with a wide range of masses and would have had a head start of billions of years over any black hole formed from stellar collapse. The problem is that primordial black holes remain hypothetical. There is no confirmed observational evidence for their existence, and constraints from various observations limit the mass fraction of the universe that can be in primordial black holes. Each proposed solution has a problem. Each answer generates a new question. This is not a failure of science. This is science working correctly, encountering a genuine limit in our understanding and pushing against it. The situation has become sharper in recent years, and the sharpness is uncomfortable. The James Webb Space Telescope, launched in December of 2021 and operational since 2022, was designed in part to look into the early universe with unprecedented sensitivity. It can detect faint infrared light from objects at extraordinary distances, objects at redshifts that were simply inaccessible to previous telescopes. It is the most powerful space telescope ever built, and what it has found in the early universe has been, to put it plainly, surprising. When the James Webb Space Telescope began returning data from the early universe, it found exactly the kind of thing that was already troubling astronomers. Galaxies and black holes that are too massive too soon. Objects in the first billion years after the Big Bang that should not, according to our standard models, have had enough time to grow to the masses we observe. TON 618 was already anomalous. But JWST showed that TON 618 is not alone. The early universe appears to be full of objects that challenge our growth models. Not one anomaly, but a population of them. Not a measurement error, but a pattern. What this suggests increasingly is that our models of how black holes form and grow in the early universe are fundamentally incomplete. Something happened in those first billion years. Some process or combination of processes that our current physics has not fully accounted for. The universe grew in ways we have not yet understood. And TON 618 is one of the most extreme pieces of evidence for that incompleteness. Let us do something different now. Let us stop observing from a distance and approach. This is a thought experiment, of course. No spacecraft exists or is imaginable that could cross 10 billion light-years of space. No human lifetime is long enough to witness the journey. But thought experiments are real scientific tools. They clarify the physics, force the imagination into contact with the actual implications of the equations, and sometimes reveal things that pure calculation does not make vivid. You are approaching TON 618, not the quasar which blazed for billions of years and has likely gone dark. The black hole itself, as it exists in the universe today, a dark, silent mass. 40 to 66 billion solar masses sitting at the center of an ancient, evolved galaxy, billions of light years from anything resembling human civilization. The journey to reach it, even at the speed of light, would take 10.8 billion years. There is no technology imaginable that could make this journey in less time than that, because the distance itself is the constraint, and no spacecraft travels faster than light. This thought experiment is not a plan. It is a way of thinking about what the physics actually implies for an object that we can measure but never visit. Call it a ghost story told in physics. The physics is real, the journey is imaginary, the conclusions are genuine. At enormous distance, there is nothing unusual to report. Space looks like space. Stars, distant and sparse. The host galaxy visible as a smear of light, unremarkable now that its central engine has shut off. You might pass through the outer regions of the galaxy without noticing anything exceptional. As you approach the galactic center, things change. The stellar density increases. Stars become more tightly packed. Their orbits become faster, pulled by the enormous central mass. If you were measuring time and distance and watching the motions of stars, you would notice the strange speeds, the tight elliptical orbits that betray the presence of something enormous at the center, invisible but gravitationally overwhelming. Closer, the host galaxy fades. You are in the sparse hot gas of the galactic nucleus. There are no stars close to the center. They have been disrupted, consumed, scattered. The region immediately surrounding the event horizon is relatively clean. The accretion disk that once blazed here has drained. The jets are off. And then, at a distance of 1,300 astronomical units from the center, you reach the event horizon. You might not notice. This is the paradox of a black hole this large, and it is genuine, not rhetorical. At the scale of TON 618's event horizon, the tidal forces, the difference in gravitational pull between your head and your feet, are extraordinarily gentle. Tidal forces are what cause the spaghettification effect, the stretching and eventual disruption of objects that venture too close to a black hole. For stellar mass black holes, tidal forces become lethal at distances vastly larger than the event horizon. You would be torn apart long before you crossed the boundary. For a supermassive black hole like the one in M87, with its 6.5 billion solar masses, tidal forces at the event horizon are already relatively mild, probably survivable for a very brief period. For TON 618, with its mass 10 times larger, the tidal forces at the event horizon are weaker still. At the scale of a human body, the difference in gravitational pull across the distance of your height, at the moment you cross the event horizon, is negligible. Not zero, but not enough to be felt. You would cross the event horizon and feel nothing. The universe outside would look much as it always had. Stars, light, the familiar geometry of space. The crossing is not dramatic. There is no dramatic appearance. There is no wall of fire, no visible boundary, nothing to indicate that you have just crossed the most consequential threshold in the known universe. What has changed is your future. Inside the event horizon of a black hole, the relationship between space and time is reversed in a way that has no analog in ordinary experience. Outside the event horizon, you can choose your direction in space. Move toward the black hole or away from it, orbit it, or flee from it. Your spatial position is something you have some control over. Time, on the other hand, moves in one direction only. The future is mandatory. You cannot choose not to age. You cannot return to the past. Time flows in one direction, and all futures, however they differ in their spatial characteristics, share the property of moving forward in time. Inside the event horizon, this is reversed. The singularity, the center of the black hole, is not a place in space. It is a moment in time. It is the future, and it is mandatory. All paths inside the event horizon, regardless of their direction in space, regardless of any force you apply, lead to the singularity. You cannot avoid it the same way you cannot avoid tomorrow. It is in your future, and you cannot choose a path that does not reach it. The singularity of TON 618, given the size of its event horizon, is not immediately accessible. Even at the speed of light, crossing the event horizon to the singularity would take weeks. A traveler with normal propulsion would experience months or years of subjective time between crossing the horizon and reaching the end. Weeks of travel inside a black hole, in a region that looks, for much of that time, like ordinary space. What does the universe look like from inside? As you fall inward from the event horizon, the outside universe would still be visible. Light from outside can cross the event horizon inward, though nothing can cross it outward. This asymmetry is fundamental. The event horizon is a one-way membrane for information. From the inside, you would see an increasingly compressed view of the entire universe, mapped onto a shrinking region of sky in the direction behind you. This compression happens Because the geometry of space-time inside the event horizon is increasingly distorted. Light that entered the event horizon at different times from different directions all arrives at your location at different angles, and as you move deeper toward the singularity, the cone of sky in which the outside universe is visible narrows. The universe behind you appears increasingly blue-shifted, compressed, bright. In front of you, in the direction of the singularity, there is nothing. No light arrives from that direction because nothing can escape from deeper inside. The experience is unlike anything in ordinary physics. You are falling, but there is no sensation of falling. You are inside the most extreme gravitational environment in the known universe, but the tidal forces that would betray that to your body are still, for much of this journey, weaker than you might expect. The gentle giant paradox holds here too. At ton 618 scale, the violent physics is concentrated near the singularity, not spread across the event horizon. For most of the journey from the event horizon to the singularity, which at light speed would take weeks, the experience would be one of strange, quiet, increasingly disorienting observation. The universe compressing behind you, the geometry of space twisting in ways that have no analogues in ordinary experience. And ahead, the singularity, getting closer in time, whether you move toward it spatially or away from it. You cannot move away from the singularity. That is the point. It is in your future. It is mandatory. The light from outside would be blue-shifted, shifted to higher energies as it falls down into the gravitational well you now occupy. You would see the universe speeding up, stars and galaxies flickering through their evolutions at accelerating rates. Not their actual present, but a cascade of ever-fresher light arriving from outside. Eventually, as you approach the singularity, tidal forces that were negligible at the event horizon would grow extreme. The difference in gravitational pull across your body would become significant, then painful, then catastrophic. The process of spaghettification, so dramatic at the event horizon of small black holes, is merely delayed at ton 618, not eliminated. It waits for you deep in the interior, where the density gradient finally becomes steep enough to be felt. And then the singularity. The singularity is where our description of the universe fails. General relativity, Einstein's theory of gravity, the theory that predicted black holes, the theory that has been tested to extraordinary precision by every experiment and observation we have been able to perform, produces infinities at the singularity. Infinite density, infinite curvature of space-time, infinite tidal forces. When a physical theory produces infinities, it is not telling you that infinity actually exists. It is telling you that the theory has reached the limit of its applicability. The equations are breaking down because the physics is doing something for which the equations were not designed. We have two extraordinarily successful theories of physics: general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which describes the behavior of matter and energy at very small scales. In almost all circumstances, these two theories operate in separate domains and do not need to be reconciled with each other. But at the singularity of a black hole, both theories become simultaneously relevant, and they are irreconcilable. They predict contradictory things. They cannot both be right. The resolution to this contradiction is a theory of quantum gravity, a theory that successfully unifies general relativity and quantum mechanics. No such theory currently exists in a complete, experimentally tested form. String theory and loop quantum gravity are candidates, but neither has been confirmed by experiment. At the singularity, we do not know what happens. We genuinely do not know. It is one of the most fundamental open questions in physics. What replaces the singularity when quantum gravity is properly accounted for? Is there a bounce, a collapse that reverses? Is there something like a wormhole connecting to another region of space-time? Does information persist in some form, or is it irrecoverably lost? We have equations for stars being born. We have equations for galaxies colliding. We do not have equations for what happens inside. And here is something worth saying explicitly. As we prepare to step back from the interior of TON 618 and look at it from the outside one final time. The fact that we have gotten this far is remarkable. We detected a faint blue dot on a photographic plate in 1957. We measured its redshift in 1976. We estimated its mass in 2004, and again with improved methods in 2019. We can describe what happens to an observer falling into it. We can calculate how long it will take to evaporate. We can extrapolate its existence billions of years into a future that no living thing will witness. All of this from a point of light in the sky. All of this from photons that traveled 10.8 billion years to reach our instruments. All of this from measurements made by human beings using instruments built on a small rocky planet orbiting an unremarkable star on the outskirts of a galaxy that is not particularly notable among the 2 trillion galaxies, observable universe. The tools of science, optics and spectroscopy and radio receivers and digital detectors and mathematical physics have allowed us to reach across a significant fraction of the observable universe and extract real information about one of the most extreme objects that exists. We cannot visit it. We cannot send a probe to it in any timescale relevant to human civilization. But we can know things about it, true things. Things grounded in observation and theory that has been tested and refined over a century. That is what we have built. That capacity for knowing at a distance, for extracting truth from ancient light, is one of the most remarkable things about the species that noticed a faint blue dot in Mexico in 1957 and eventually asked what it was. We do not have equations for what happens at the singularity, but we got a long way. We got surprisingly, improbably, wondrously far. There is one final puzzle worth naming before we leave the interior of TON 618. One of the deepest and most contested questions in modern theoretical physics. The information paradox. Quantum mechanics rests on a principle called unitarity. In quantum mechanics, information is conserved. If you know the exact quantum state of a system at one moment, you can in principle calculate its exact quantum state at any other moment, past or future. Information is never created or destroyed. It can be scrambled, encoded, transformed, but it cannot vanish. A black hole appears to violate this principle. Matter falls in. The matter carries information about its composition, its structure, its quantum state. The event horizon seals it off from the outside universe. When the black hole eventually evaporates, through the slow emission of Hawking radiation, the radiation that comes out appears to be purely thermal, carrying no information about what fell in. The information appears to have been destroyed. Stephen Hawking argued for decades that information was indeed destroyed, that black holes fundamentally violated quantum mechanics. Many physicists found this deeply unsatisfying. Quantum mechanics is one of the most precisely tested theories in the history of science. The idea that it would simply fail at a black hole event horizon was not impossible, but it was uncomfortable enough to motivate enormous theoretical effort to find an alternative. The tension between Hawking radiation, the possibility of black hole evaporation, and the conservation of information is called the information paradox. It has been one of the most intensely studied problems at the intersection of quantum mechanics and general relativity for decades. It has motivated proposals ranging from firewalls, the idea that the event horizon is not gentle at all, but a wall of high-energy radiation that destroys infalling observers, to fuzzballs, a string theory concept in which the singularity is replaced by a diffuse quantum structure, to the holographic principle, the idea that all the information inside a black hole is somehow encoded on its two-dimensional surface. Hawking eventually revised his view. In his final years, he proposed that information might be preserved in what he called soft hair, subtle quantum correlations on the surface of the event horizon, scrambled beyond any practical recovery, but technically conserved. Whether this actually resolves the paradox is right? The theoretical community has not reached consensus. The question is unresolved. It is one of the most fundamental open questions in physics, and it is not abstract. It bears directly on some of the deepest questions about the nature of reality. If information can be destroyed, quantum mechanics as we know it is incomplete. If information is conserved in some form, we need to understand exactly how, which requires a theory of quantum gravity we do not yet have. Ton 618 will evaporate eventually. Not soon, not by any standard of time that has meaning for us, but eventually. And when it does, what becomes of all the information it has consumed over its existence? The stars, the gas clouds, the planets, perhaps the civilizations, all the matter and energy and structure that fell past its event horizon over billions of years? This is an open question, one of the most fundamental ones in physics, and Ton 618, the most massive black hole we know of, will be the last to answer it. The universe has a long future, not infinite, but long enough that any attempt to feel its full extent runs into the same cognitive failure we encountered with Ton 618's mass. Numbers at this scale stop working the way numbers should. We have already established that human intuition fails at large numbers. What we are about to discuss is not just large numbers. It is numbers so vastly larger than the numbers we have already been using that the comparison itself becomes absurd. The current age of the universe is approximately 13.8 billion years. That is a number we have been using throughout this video as a reference point. 13.8 billion years. The universe is 13.8 billion years old. Everything we are about to discuss is longer than 13.8 billion years by factors so extreme that we need scientific notation just to write them down. The current age of the universe, in terms of the timescales of the far future, is nothing. It is less than the first tick of a clock that has not yet started. The far future of the universe is one of the most remarkable things that physics has produced. It follows, with considerable confidence, from physical laws we understand well. It is not speculation, it is extrapolation. Extrapolation so far into the future that it begins to feel like science fiction. But extrapolation grounded in real physics. Let us follow it to its conclusion. Before we follow the universe to its conclusion, it is worth pausing on something. The universe we have been describing throughout this video, the universe of blazing quasars and colliding galaxies and star formation and the gradual accumulation of complexity, is a universe in its youth, not quite infancy, but youth. We are living through the stelliferous era, the age of stars, which began a few 100 million years after the Big Bang and will continue for roughly another 100 trillion years. During this era, stars are forming, galaxies are evolving. The cosmos is lit from within by the fusion reactions of countless nuclear furnaces spread across 2 trillion galaxies. It is an active, living, light-filled universe. We are in the middle of that era. Not the beginning, but nowhere near the end. The universe is 13.8 billion years old. The stelliferous era will last approximately 100 trillion years. We are in the first 0.014% of the age of stars. The night sky, as we know it, full of stars and galaxies, bright and complex, is not the default state of the universe. It is a brief episode. What follows it is almost incomprehensibly different. In approximately 5 billion years, our sun will exhaust the hydrogen at its core. It will expand into a red giant, consuming Mercury, Venus, and possibly Earth. Its outer layers will disperse into a planetary nebula. What remains will be a white dwarf, an Earth-sized remnant of dense hot carbon and oxygen, slowly cooling over billions of years. In approximately 100 trillion years, the last stars in the universe will exhaust their fuel and go dark. This will not be a single event. It will be a gradual dimming as the most massive stars die first, followed by medium stars like our sun, followed by the red dwarfs, the smallest and most long-lived of all stars, which can continue burning for tens of trillions of years on their modest hydrogen reserves. The last red dwarfs will go out like candles, not in any dramatic explosion, but simply running out of fuel, cooling and dimming over geological timescales until they are no longer producing fusion energy and become brown dwarfs and eventually black dwarfs. The era of stellar light, which began a few 100 million years after the Big Bang and which we are currently in the middle of, will end. The night sky will not go dark all at once. It will fade. Each galaxy will grow dimmer as its stellar population ages. The intergalactic medium, lit by radiation from star-forming regions, will grow cold. The cosmic inventory of light will dwindle as there are fewer and fewer nuclear furnaces to produce it. When the last star goes out, the universe will be very old and very dark. The concept of a night sky, a sky with points of light, will be as alien to any hypothetical observer at that time as our concept of a world without stars is to us. We have never experienced a universe without stars. We were born into a universe ablaze with stellar light. The universe without stars, the universe that will exist for the vast majority of its existence, is something we can describe but not feel. The universe will enter what cosmologists call the degenerate era, a vast, cold, dark age populated by white dwarfs and neutron stars and black holes, the remnants of the stellar age, slowly radiating away the energy stored during the cosmic youth. In approximately 10 to the power of 40 years, even the remnants of stellar evolution will have decayed. Protons, the constituent particles of atomic nuclei, are theorized to be unstable on very long timescales, eventually decaying into lighter particles. If proton decay occurs on this timescale, then all matter made of ordinary atoms will eventually dissolve. In approximately 10 to the power of 67 years, black holes of stellar mass will have evaporated completely through Hawking radiation. They will have shrunk over inconceivable spans of time, losing mass in a trickle of thermal radiation until they finally vanish in a brief burst of high-energy particles. Ton 618 is different. Let us take stock of where the universe is when we reach the point at which the last stellar mass black holes are evaporating, approximately 10 to the power of 67 years from now. There are no stars. The last star died approximately 10 to the power of 14 years ago. The concept of starlight of a night sky filled with points of light, of a galaxy visible as a band of luminosity across the sky, is so ancient at this point that there is no meaningful way to call it history. It is archaeology of a kind that the universe itself has largely erased. There are no planets. Planetary systems dispersed long ago as their host stars died and the gravitational bonds holding the solar system together frayed. The atoms that once composed planets have been scattered into the vast cold darkness of intergalactic space. There are no atoms, in the conventional sense, if proton decay has occurred. The protons that constitute the nuclei of ordinary matter have decayed into lighter particles. The matter you are made of, the matter that makes up everything you have ever touched or seen or thought about, has dissolved. Not destroyed, the energy is conserved, but the structure is gone. What remains at 10 to the power of 67 years is black holes. Just black holes, of various masses at various stages of their evaporation. Stellar mass ones are ending now. Supermassive ones have much longer to go. And TON 618, the most massive one we know of, has barely begun. Hawking radiation is incredibly slow for a massive black hole. The rate of mass loss is inversely proportional to the square of the mass. A more massive black hole evaporates more slowly, much more slowly, enormously, incomprehensibly more slowly. For a black hole of TON 618's mass, the Hawking evaporation timescale is approximately 1.3 times 10 to the power of 99 years. That is a number with 99 zeros after it. It is not a number that can be felt or intuited. It is so vastly larger than the current age of the universe, which is approximately 10 to the power of 10 years, that the current age of the universe is essentially zero in comparison. It is so vastly larger than the timescale for proton decay that ordinary matter will have long since ceased to exist. It is larger than the timescale for stellar mass black hole evaporation by 32 orders of magnitude. In a universe so cold and dark and empty that the concept of a star would be ancient mythology, in a universe where the atoms that make up your body have long since decayed, in a universe where the last echoes of the era of galaxies have faded billions upon billions of years into the past, TON 618 will still exist. It will have consumed whatever remained within its reach. It will have grown, perhaps, though, in the cold, sparse universe of the far future, there will be little left to consume. It will sit in silence, a dark mass, indifferent to the passage of time in the way that only the most extreme objects in the universe can be. And eventually, after 1.3 times 10 to the power of 99 years, it will end. A slow trickle of Hawking radiation, indistinguishable from the background noise of a dead universe. A last flicker of energy as the remaining mass converts to radiation in a final brief burst. Then nothing. The largest, most massive, most enduring object in the observable universe, the object that outlasted every star, every galaxy, every other black hole, gone. A remnant of the age when the universe was alive and full and blazing with light. Two astronomers in Mexico, 1957, a photographic plate, a faint blue dot, described only as decidedly violet. They wrote it down. Entry number 618 inches. The Tonnant-Zintler catalogue filed it away. There is something worth noticing about the relationship between that moment and everything we have discussed since. The light on that photographic plate had left its source 10.8 billion years before it arrived at Tonnant-Zintler. It had crossed an incomprehensible fraction of the observable universe. It had survived the expansion of space, the passage of time on scales that dwarf the existence of our solar system, the long dark journey from a blazing quasar in the early universe to a quiet observatory in the Mexican highlands. And then two people looked at it, noticed it, wrote it down. That is also remarkable, though in a different way from the object itself. That the universe should produce, in one location, a black hole 40 to 66 billion times the mass of our Sun, an object that blazes with the light of 140 trillion suns, an object whose event horizon would swallow everything we have ever known, an object that will outlast every other structure in the observable cosmos, and that the universe should also produce, in another location, beings with eyes and brains and scientific instruments and curiosity, beings capable of noticing that faint blue dot and writing it down and asking what it is. These two things, the unimaginable extremity of Ton 618 and the improbable existence of the creatures who discovered it, are both products of the same universe, unfolding from the same initial conditions, subject to the same physical laws. We are made of star stuff, as Carl Sagan said. We are made of the elements forged in stellar interiors and distributed by stellar deaths. We are the universe looking at itself. And one of the things the universe has found, when it looked at itself, is Ton 618. A black hole that should not exist by any model we have. A black hole that will outlast everything. This fact that we exist, and that Ton 618 exists, and that we can look at it and measure it and try to understand it, is worth holding for a moment before we let it go. The universe does not require observers. It does not require anything. It simply is, operating according to physical laws that exist independently of whether any conscious entity ever comes to know them. Ton 618 would have formed without us. It would have blazed as a quasar for billions of years without us. It would have gone dark and settled into its current silence without us. It will evaporate in 1.3 times 10 to the power of 99 years, without any successor to us, in a universe so transformed from the current one that the concept of observation will almost certainly not exist. We are a parenthetical in the timeline of TON 618, a brief episode. The universe was already 10.8 billion years old when the light we see from TON 618 was emitted. By the time Ton 618 finally evaporates, the current age of the universe will be so negligible that no meaningful comparison is possible. We exist in a sliver of time so thin that on the full timeline of Ton 618, we might as well not exist at all. And yet we noticed it. Two people in Mexico in 1957, working carefully and methodically through a photographic catalogue of faint blue objects, wrote down the number 618. And what followed over the following decades is the story of the human species extracting truth from ancient light, measuring the redshift, calculating the luminosity, estimating the mass, realizing it should not be this massive, asking why, building new telescopes to look deeper, finding more objects like it in the early universe, pushing the boundaries of theory to try to explain what the observations are showing us. That process is not finished. It will not be finished in any of our lifetimes, but it is continuing. And what it has produced so far, the picture of Ton 618 and what it implies about the universe, is one of the most extraordinary things the scientific enterprise has ever assembled. A faint blue dot, decidedly violet, written down and filed away, waiting to be understood. They could not have known. They had no tools to know. The concept of what they had found did not yet exist in the vocabulary of science. A black hole, 40 to 66 billion times the mass of our Sun. An event horizon that would swallow our entire solar system. A luminosity of 140 trillion suns. A light that had been traveling for 10.8 billion years before it reached their photographic plate. An object that should not exist by any model we had in 1957, or in 1990, or in 2024. An object that poses questions we do not yet know how to answer about how the universe grew, about what happens at the center of a black hole, about whether information is preserved or destroyed, about the ultimate fate of the most massive structures the cosmos can produce. An object that challenges our best models in ways that will drive new physics, new instruments, new understanding that we cannot yet predict. An object that has outlasted the quasar phase, outlasted the era of rapid galaxy formation, outlasted the period in which its own blazing light was produced. An object that is, right now, dark and silent and waiting in the center of an ancient galaxy, millions of years from anything resembling human civilization, indifferent to its own existence in the way that only the most extreme objects in the universe can be indifferent. An object that will outlast everything. The universe is 13.8 billion years old. It is full of things we found by accident, things we did not understand when we found them, things that defied our best models and forced us to build better ones. It has never, at any point in the history of science, turned out to be smaller or simpler or less strange than we thought. Every time we built a better instrument, we found something that required a bigger idea. Every time we answered a question, we found 3 more questions hiding behind it. Every time we thought we understood the scale, the universe expanded again. It will continue to be full of such things for longer than any number we can comfortably write. Ton 618 was waiting to be understood. It is still waiting. And in the silence of a future universe, incomprehensibly remote from this moment, long after everything we know and everything we are has dispersed and decayed, long after the concept of a star is ancient mythology, long after the last stellar mass black hole has evaporated, and the universe has entered a darkness so complete that there is nothing left to cast a shadow, something that began as a faint blue dot on a photographic plate in the highlands of Mexico will still be there. Not blazing, not feeding, not producing the light of 140 trillion suns, just existing. A mass, a geometry, a remnant. Waiting. In 1.3 times 10 to the power of 99 years, it will end. A flicker of Hawking radiation, a last whisper of energy in a universe that has been silent for unimaginably long. And then, nothing. The end of the oldest, heaviest thing that the observable universe ever produced. And no one will be there to see it.